So welcome to module 10 of the Pawsey user training series on testing job runs. So this is module 10 out of 11 of the Supercomputing user training series. This is quite a small, compact module with just limited outcomes, still quite important for you to be aware of. So why do we need to test job runs? How to optimize the resource requests for the scheduler, and how to use information on total job runtime and total job cost in terms of counting. We're using in this module, we're using knowledge and terms that we covered in previous modules, in particular training 8 and training 9 on the job scheduler and running jobs. Watch out for the signs of the presentation. They highlight key callouts for the module. So why is it useful to test job runs in a supercomputer? There can be, we identified the 3 key cases for testing job runs. So the first one is to make sure that any bash script, any computational workflow you submit for the first time is correct in terms of syntax of the script, in terms of the resource request, in terms of how the program is configured to run. This is a good habit just to avoid wasting computational resources. But there are other cases. So one is to optimize resource requests, in particular wall time and size of node, task, and CPU requests, as well as memory size. And another quite important user case when preparing a merit application. So to write and submit a merit application for using Pawsey resources, you will need to produce data to demonstrate scaling of your scientific workflow. So this will make your application stronger. And so it's important in this context, it can be useful to know how to run meaningful test runs to this end. So let's quickly talk about these 3 scenarios. So the first one was testing a job run for the first time. So the goal here is just to make sure that the job run as intended. You have a couple of options, actually. The first one is written here. So you can inspect just the production job itself. You verify, before you submit it, you just verify the contents of the scripts in terms of the scheduler directives, the SBatch lines, and also the shell commands that make up the actual workflow. Verify any other input file that comes with the workflow. And then after the job starts, monitor the output in real time to make sure that it's going as intended. Now there's a second way of playing these test runs, which is not currently written down here in the slide. So if the production run is very large, it might take a while until the scheduler executes it. So if your intent is just to test the correctness of the setup and syntax, you can actually schedule the job with a shorter wall time, and if possible with a smaller resource request. So that way it will be more likely to run sooner rather than later. And if the request is small enough to fit in the debug queue, you might even be able to submit it to the debug queue and have it running for the test, for the purpose of testing very soon, just for checking that the output is correct. Let us now move to the second case, so optimizing resource requests. This is quite important. I mean, this is both about ensuring that the requests match what you actually need, which means that the scheduler will be scheduling your job for execution in the best possible way. But this is also about eventually selecting an optimal number of nodes and CPUs for your job so that you can get the answer faster with a reasonable cost in terms of service units. Let's talk first about the maximum duration, so the wall time option. So you want to identify the optimal one. So if you underestimate it, it means the job will not complete within the allocated slot by the scheduler. So you won't get the answers at all. You might need to rerun it again, so that's not good. But also overestimating it too much may imply that the scheduler will let it wait for longer in the queue because it will need to find a largest spot in the planning of the usage of the resources. So it's good to be able to have a good estimate of how much the job needs to run for. So you can play it in a couple of ways. So you could run your job with maximum wall time for the first time, see how much it takes, and then adjust the subsequent runs accordingly. Or in alternative, you can configure a job to just run for a fraction of the total simulation length. And this applies specifically to workflows where there is an iterative component. So you can just, if you have, say, 10,000 iterations, you can just let it run for 10 and use the duration required for the subset of iterations, extrapolated to get the full required wall time. In some workflows, you may even be able to scale the size of the problem down and still be able to get a meaningful estimate for the total duration. This actually only applies if you know that the total wall time is linearly proportional to the size of the problem. Otherwise, this second option is not really viable. If you then also optimize for CPU, task, and node count, as you will see in the next slides, you may need to reassess the wall time after that as well. In this slide, I'm also covering the case of memory requirements. So here the advice is really just, okay, start your workflow with a default value, which will suit most cases. If the job gives an out-of-memory error, then that's the case for increasing the memory request by specifying the mem flag explicitly, and increase the request in a progressive way until the job can run successfully. Keeping in mind that the default, more or less, is 1.8 gigabytes per core. And also keeping in mind that what you need to provide here is the per node count. So there is just a bit of math involved. Okay, let's now talk about optimizing resource requests in terms of nodes and task and CPU count. Let's take the case of an MPI application first, an application that runs over multiple processes, which implies it will need to request for multiple tasks and possibly multiple nodes. So that's the focus for this case, number of tasks and nodes. We recommend to start from 8 tasks in a node. This is the one cache domain for optimal performance, as I mentioned in training 8, running jobs. So you do one short run with you do one run with 8 tasks, and then you progressively double up the number of tasks in one node. So 16, 32, 64, 128. Eventually, you can keep doubling up then the number of nodes. So keeping the tasks per node 128 and keep on growing the number of tasks. What's the rationale here? Well, the rationale here, there will be a nice graphical slide soon, is to record the runtime of the computational intensive component of the job. So keep track of how much it takes with the various setups, and also keep track of the total cost, which means the runtime times the number of used cores. And we're going to see how to use this information soon. Before seeing that, there's also the example of an OpenMP, of a multi-threaded application. In this case, the key quantity is CPUs per task. You start from 1 CPUs per task, and then you go up. Probably it's a good idea. Yeah, go up in powers of 2 for 8 up to 128, which is the maximum number of cores per node. And again, similar to the MPI case, record the runtime, the total cost, which means runtime times the requested cores. And then what are we doing with that information in either cases? Well, you can then draw nice plots. And here I'm just showing you the example with an MPI run of a molecular dynamics benchmark run of a box of water molecules with 800,000 atoms with the LAMMPS code. But this is a benchmark I use a lot myself for testing purposes. But it gives us a good idea of how to assess this optimization of resource requests. So here, keep in mind here the benchmark in this case was run on Magnus, our previous supercomputer. So the reference run was with 24 processes, MPI processes, for one node of Magnus. Here we go. So I was mentioning to record the runtime and the total cost. of your trial runs. So the runtime is just how long it takes to run, and the total cost is the runtime times the requested cost. And as you can expect, if you increase on the x-axis here, we have the process count, so the number of MPI tasks, which also maps to the number of requested cores in the case of pure MPI applications. And as you can expect, the runtime goes down as you use more resources. This is an MPI application, so it's able to exploit parallelism of multiple processes. But if you have a look at the total cost, so this is what gets charged on your compute allocation. So when you, in this specific case, when you go up to say about 1,000 processes or so, what you're paying compared to using just one node or 24 processes is just 1.5 times that amount. And you can see this on the y-axis. So 1,000 cores is about 1.5 factor in total cost. And for that cost, so just for 50% more, you get quite a huge speed up. Actually, if you have a look here, you are around probably a 20 times speed up in the time it takes to get the answer for 1.5 extra cost. So it's kind of worth it. But then as you increase the number of process counts, that total cost goes up quite quickly and sharply. And that's because no parallelization in the algorithm is ideal. You always have a cost in the algorithm due to parallelizing, so communication costs and other overhead. And so that cost goes higher and higher as the number of processes grow. And same with OpenMP, the number of threads grow. And so when you want to optimize your resource request, it's really just a question for yourself. So how much extra computational cost in my allocation am I willing to take to get the answer faster? And that's how in the end you end up tuning your resource request. With the very same information that I mentioned, so runtime cost and total cost, you can also draw plots to demonstrate scaling of your application. And here the goal is, as I was mentioning, merit allocations to get time on the supercomputer. So there are actually two types of scaling that we can talk about. Weak scaling means you are increasing the core count that you're using, but also the program size. So say you're throwing a plot where you are doubling up the number of cores at every run, but you're also doubling up the problem size. But then there is a strong scaling, which means you're increasing the core count, but the problem size is the same. The weak scaling is kind of a requirement that is relatively simple to achieve in algorithms. The strong scaling is the difficult one. So there are comparatively less algorithms that are capable of strong scaling compared to those that are capable of weak scaling. And in this example, I'm just going to focus on the strong scaling example. So same problem size, same input, just increasing the core count and see what we can get. There are two measures here to record scaling. The speed up is just the inverse of relative runtime. And this needs to be computed relative to a reference run, so relative to running on one node, for instance. And then there is the efficiency, which means the speed up that you just computed divided by the ideal speed up. And what is the ideal speed up? Well, in an ideal parallel world, if I use double the cores, it takes me half the time to get the answer. If I take 4 times the cores, it takes me 1/4 of the time to get the answer. This is the ideal speed up. Then there is the real one. Let me show you the example with the very same benchmark with lamps that I showed in the previous slide. So the plot on the top is a strong scaling speed up plot. And I also, for your convenience, I also plotted this line, which is the ideal speed up. And you can see that for relatively low process count or core count, say up to 500, the speed up is quite close to ideal. And then it diverges from that as you increase the process count, because, as I said in previous slide, the parallelism comes at a cost. Algorithms are not scaling in an ideal way. There's always some hit, some overhead. You can also see that in terms of efficiency, the second quantity I mentioned. In the reference run, we have 100% efficiency, and as you go up in process count, in core count, the efficiency inevitably drops. Say we are still around 70%, in this case for 1,000 processes, but then it drops lower and lower. And so in terms of a merit application for compute time on photonics, of course, the higher the efficiency or the better the speed up at a high process and core count your program has, and the stronger the application will be. And that's one of the ways applications are actually ranked. Just to summarize on this little module, we talked about why it is useful to test job runs and how to optimize resource requests. So in terms of duration, memory requirements, and job size. And we also discussed the merits of considering job runtime versus total job cost, depending on the urgency of your runs. And finally, we also covered the aspects of scaling plots for the purpose of demonstrating scaling of your application. So on the Pawsey support portal, we have extensive documentation on many areas covered in detail. We also have a user support portal in case you need help and need assistance from Pawsey staff with your issues. If you want to stay up to date with news and events from Pawsey, you can sign up for the Pawsey Friends newsletter. Thank you for your attention. The module is finished and the session is open for questions.